to talk about our exciting plans to build a dedicated forward physics facility at the high luminosity LHC. So I would like to start with a quick introduction. It feels a little bit like preaching to the choir here, but let me remind you why a forward physics facility is interesting for astroparticle physics and what are the synergies between these plans and astroparticle physics. So as we all know, the properties of the initial cosmic rays are inferred indirectly by comparing our data to simulations. And we are all familiar, we have seen many of these kind of plots that Auger reported, for example, a deficit in simulations in the muon number, where we basically see roughly 30% more muons in data than predicted by simulations. What you see here is a picture from the WISP working group, where we basically have this kind of collection of all global muon data over 3 to 4 orders of magnitude and energy. And we show the muon numbers in this Z scale, where basically if our data agrees with simulations of proton showers, the Z value is 0. If it agrees with simulations of iron showers, the Z value is 1. And what you see here at the highest energies, for example, is that the data indicates a composition that would be heavier, significantly heavier than iron, which doesn't really make sense. This holds for basically all the models. So in each of these panels, you see a different hadronic model in comparison to the data. And none of these models, at least at the highest energies, seems to describe the data correctly. This introduces large uncertainties in the interpretation of cosmic ray data. For example, if you want to infer the composition of cosmic rays, these kind of discrepancies between simulation and data introduce large uncertainty. Another important aspect in terms of synergies with the forward physics facility is the background for high energy astrophysical neutrino searches, where basically, as you see here in this picture from IceCube, the dominant background for these astrophysical neutrino searches is neutrinos from, or atmospheric neutrinos from prompt decays, meaning basically or mainly from charmed hadrons. And on the right-hand side, you see theoretical predictions of these prompt neutrino fluxes. And here you see that basically predictions range over roughly 1 order of magnitude in terms of the normalization. And you also see for certain models these uncertainty bands, which are basically roughly an order of magnitude. So you have large uncertainties on these neutrino fluxes, which causes, or which is the dominant uncertainty in, for example, astrophysical neutrino fields. So we have seen that yesterday already in Matthias' talk. The dominant uncertainty in searches for astrophysical neutrinos is the uncertainty from prompt neutrino fluxes. So why is that? What is the challenge in describing these processes in air showers correctly? And one of the main caveats is that the particle production in air showers is mainly in a forward direction. And if you, for example, look in this picture where you basically see the pseudo-rapidity distribution of different hadrons, I would like to point you to these dashed lines. These are basically, if you assume that these hadrons propagate through the atmosphere and decay into muons, these are the corresponding pseudo-rapidity distributions. So the main particle yield in air showers is produced from pseudo-rapidities above roughly 7. You also see these dashed lines, which show you the coverage of LHC experiment currently. And as you see, the coverage at pseudo-rapidities above 7 is very sparse. There's only LHCF, we have heard about that this morning, that measures neutral particles, but it's very challenging to measure particles at the LHC in the far forward direction. There are additional problems. It's not only that we don't have measurement, but typically we have heard yesterday, we are in the soft QCD regime. So these interactions happen at low momentum transfer. So we are not in the perturbative regime. So we don't even have first principle calculations of those processes typically, at least for light hadrons. it's more complicated because we don't only have proton-proton collisions like at the LHC, but it's a very complex particle composition in air showers. We have pion secondary interactions. And of course, we have energies ranging over many orders of magnitude. So all that makes the modeling of air showers quite challenging. And our proposal is basically to build a forward physics facility with a suite of experiments that covers the pseudo-rapidity region above 7 in the far forward direction. So the question is here, how can we test these hadronic interactions in the forward region? And more generally, what opportunities are we actually beyond the astroparticle physics aspects? What opportunities are we currently missing at the LHC from the lack of forward coverage with the current detectors? Of course, for us, more important, or in air shower physics, how can we actually test our air shower models in the far forward region? And we know that by far the largest flux of particles at the LHC is produced in the forward region. It just goes into the beam pipe and is never measured by any of those experiments. So our proposal is to build this forward physics facility right in the line of sight of the Atlas detector, separated by several hundred meters of rock, to be able to measure particle production in the forward region. Currently, there are already 3 detectors exploring the potential of forward physics at the LHC, namely SND and Phaser and Phaser New that we will hear about this afternoon. They are currently taking data separated several hundred of meters from the interaction point of Atlas. They have extremely low background, and therefore they are perfect facility or perfect experiments to measure rare processes like exotic physics, BSM physics, but also neutrino physics, of course. Our proposal is to build a dedicated facility that looks roughly like that. Right here, we found a free spot on CERN ground, actually, where we propose to build the facility roughly 630 meters away from the Atlas interaction point to measure neutrinos that are produced at the Atlas interaction point and potentially BSM physics. So this is a rough overview of the facility. It's basically a multi-purpose facility that houses several experiments in the line of sight, separated by several hundred meters of rock. And currently we propose, so here's the line of sight. And right there, like 10 meters away from the LHC tunnel, roughly, we propose to build this roughly 60, 70 meters long facility. We propose currently 4 experiments, namely Phaser 2, Phaser New 2, which are successors of the currently running Phaser detector, a new detector Flare, and Formosa. I don't want to go into too much details about the detector technologies here. I refer you to this paper, which gives a very comprehensive overview of those. Just to walk you through them very quickly. So Phaser 2 is a magnetic tracking spectrometer, which is designed to detect light weakly interacting particles. And we're going to hear about neutrino detection this afternoon. Phaser New is an emulsion detector to detect neutrinos at TeV energies. Flare is a new 10-ton scale liquid argon detector, which is basically TPC to detect neutrinos and dark matter. And then there's one dedicated detector, Formosa, which is composed of basically simple scintillating bars to detect milli-charged particles. This is my shameless propaganda slide. I want to give you an example of the physics capabilities of such a facility. So there was actually a pilot detector to test the potential for Phaser, which you see here. It was a suitcase-sized detector and took 4 weeks of data. It didn't cost a single cent because it was produced from recycled parts, and it detected 6 neutrino candidates. If you compare that against all previous collider experiments, which are building size, took decades of data, costed billions of dollars, they detected 0 TeV neutrino candidates. So with that simple detector, we kind of showed the potential for such a forward physics facility. As I said, currently PHASER is taking data, and they just reported, PHASER and S&D collaborations reported the first detection of TeV neutrino candidates last year. So PHASER detected 153 neutrinos with a significance of 16 sigma over the background. And in total, they expect to, in the 2 years of data taking, to detect roughly 10,000 neutrino candidates. We're gonna hear more about that this afternoon. If we move to a forward physics facility that would start taking data in the 2030s at the high luminosity LHC, we expect on the order of millions of neutrino, TeV neutrino candidates, and a huge muon flux that I will talk about a little bit later. So this is the location or the site that I showed before for the facility. These are the ground buildings, and below that there's going to be a shaft. Actually, we already took some cores at the site to see if the rock can accommodate this facility. And so far, all the studies look very good. So we're going to be able, from a civil engineering point of view, to build the facility there. And maybe as a private note, as someone who works mainly in IceCube, I find the perspective to actually have a site that I can just go on a plane and touch the detector. This is a great perspective. So let me talk about the physics program of the Forward Physics Facility. It's actually a huge community effort with a very, very diverse physics program. We kind of try to compile that in this picture. So there are different kind of working groups working on new particle physics, neutrinos, QCD, dark matter searches, but also astroparticle physics, as you see here. And in this talk, I will only talk about the particle physics aspect, because otherwise I had to talk the entire day, I guess, to cover the entire physics program. If you are interested actually reading about it, we had 2 very comprehensive papers. One that we call a short paper. It's not really short, it's 77 pages, but it gives you kind of a comprehensive overview. And then in the context of the SNOMAS community effort last year or the year before, we actually wrote a white paper with 430 pages, several hundred authors, that gives you a very comprehensive overview. So maybe if you're on the way back, most of you have a very long flight, and if you're bored, I invite you to take a look at those papers. This is the overview of the table of contents. You see all these describes the facility, the experiments in detail, and then many different physics scenario or physics cases that we're going to measure at the FPF. And here at the end, you actually see the last 50 or so pages are dedicated to astroparticle physics, and this is what I'm going to walk you through in this talk. So something is wrong here. Okay. As we know, most muons or most muons in air showers are produced by the decay of pions and kaons. And actually, we can measure neutrino fluxes at the FPF that are also produced by the decay of pions and kaons. And these neutrinos are basically a proxy of the pion to kaon ratio. We can study them by looking at the energy distributions, because electron and muon neutrinos populate different energy regions, which will help us to disentangle neutrinos from different origins, different hadronic decays. And moreover, they also have different rapidity distributions due to the difference in their mass, and this will also help to disentangle them additionally. So what you see here is basically a prediction from different hadronic models at pseudo rapidities above 7, where you see the differences with respect to EPOS, and you see there are quite 60% or so differences between the models in the forward region, and we will be able to see or to pin down which of the models describes the data in the forward direction the best. These are actually simulations of the neutrino fluxes that will be measured at the phasor nu2 detector. On the left-hand side, you see the fluxes of electron neutrinos. On the right-hand side, you see the fluxes from of muon neutrinos. And in different colors, you see the origin of those neutrinos. So from pion-kaon decays and from heavy hadrons. And as you see, for the different hadronic interaction models that we typically use in air shower physics, the differences are larger than roughly a factor of 2, which is way larger than the anticipated uncertainties at the FPF. So we will be able to compare the data to those models and basically test which of those models describes the data best. In order to study pion and kaon production, of course, the low energy region is the relevant region. But as we will see in a bit, in order to test heavy hadron production, we can also look at the very high energy tails to separate the neutrinos from heavy hadrons. We have already heard that just in the talk before that Alice reported a strangeness enhancement in the mid-rapidity region. So the question is, can this effect actually be seen in hadrons produced in the forward region as well? And there was a simple toy model developed by Luis Ancodocchi and his colleagues that tries to implement the strangeness enhancement with a very simple approach by just swapping pions and kaons in Sybil 2.3 and basically trying to model the strangeness enhancement this way. And this is done by with this kind of probability Fs, so the swapping or how many pions you swap with kaons is given by that Fs probability. And here on the right-hand side, you see predictions of the muon numbers for different probabilities of this swapping Fs. And as you see, in comparison to Auger data, this model is actually able to produce enough muons that it is comparable with Auger data. So that might be actually a possible explanation for the muon puzzle, because you produce more kaons, which decay into muons, so you increase the muon fluxes. And the question is if this kind of strangeness enhancement is also realized in the forward direction, and we can directly test that at the FPF. So these are simulations using this model for different swapping parameters Fs. So basically, the maximum here is you exchange 50% of the pions with kaons, which is kind of extreme. But you see the large differences in the electron neutrino and muon neutrino fluxes that would be measured in the flare detector at the FPF. And these differences are even larger than the differences between the models I've shown before. So we would be able to see this strangeness enhancement if it's realized in the forward direction directly at the FPF and constrained models. Actually, currently, we are also working towards using Sybil star, which Felix will talk about, I think, on Thursday, to check if we can see strangeness enhancement in Sybil star at the FPF. I already mentioned prompt hadron production, which is of large interest in order to understand the backgrounds for astrophysical neutrino searches and reduce the uncertainties. So if we actually look at the high energy region in the fluxes measured, in this case at phasor, you see the predictions from different models of the prompt contribution to the neutrino fluxes. And you have to take that a little bit with a grain of salt, because not all of these models really have a serious treatment of charm production, for example. But you see the differences are even larger than in the neutrino fluxes from pions and kaons. So we will be definitely able to pin down the contribution from charmed hadrons at the FPF by looking at the highest energy events measured in the experiments at the FPF. This way we can, of course, improve the model predictions and which in turn will reduce the uncertainties in astrophysical neutrino searches. One thing that I'm kind of interested at the moment is not only the neutrino fluxes, but of course we are also expecting extremely high muon fluxes at the FBF. So currently, phasor measures a muon flux of roughly 1 Hertz per square centimeter. So these are, in terms of the FBF, we expect billions of muons that we measure over the lifetime of the experiments at the FBF. While we know the origin of the neutrinos, it's kind of challenging to figure out how these muons are produced, because many of them are produced in secondary interactions in the detector or the rock. So it is kind of challenging to find out the origin of these muons, but the open questions are, can we actually use these muons to study light hadron production, for example? Can we measure a muon charge ratio, which would be interesting to constrain models? And currently there is actually dedicated muon detectors at the existing phasor experiment, which will be interesting to look into this data, because one question is we can just put up temporary detectors, simple scintillator counters for a week, and the fluxes or the statistics in our data will be extremely large already. So the question is, can we actually build dedicated muon detectors in the facility to learn something about the muon fluxes? It will be interesting to see actually the current phasor measurements, if we can learn something from those, and then this will inform a potential design of dedicated muon detectors at the FBF. What you see here is kind of what I mentioned. This is the origin of the muons measured at phasor as a function of the distance from the interaction point. And as you see here, there are certain structures where you have secondary interactions that produce secondaries, which decay into muons. And this will be challenging to kind of use them for physics. However, so this is a picture, a two-dimensional picture of the muon fluxes at the FPF. On the left-hand side, you see mu minus, on the right-hand side, mu plus, and you see all these structures. And for example, here on the right-hand side, these structures we can see in simulations. This is basically from secondary interactions in the beam pipe. And the question is, can we use these structures to isolate muons where we know the origin? And these studies are currently ongoing. Finally, because if you look into the contents of this paper, probably 200 pages are dedicated to BSM physics and searches for dark matter. So I just want to mention that there are also huge capabilities to look for BSM particles, especially long-lived particles that we would measure directly at the FPF. And there's a huge variety. We can measure the production of BSM particles, dark matter scattering, as I mentioned at the beginning, milli-charged particles, or more exotic scenarios like quarks and long-lived particles, of course. I would like to refer you to the paper if you're interested to get an overview of these searches. Which brings me to the summary. So as we all know, the measurements or the interpretation of cosmic ray measurements highly relies on Monte Carlo simulations of the air shower. And as we know, there are large discrepancies observed at the moment. The challenge is also to describe the neutrino fluxes properly for the searches for astrophysical neutrinos. And we propose to build a dedicated forward physics facility at high pseudo-rapidities above 7 to measure particle production at the LHC in the line of sight of the Atlas detector under controlled conditions. As I said, there's a very diverse program, physics program, so I wasn't able to go into all these details, but I invite you to take a look at the paper. And the goal, of course, is to reduce uncertainties by those measurements in the description of air shower physics, and in turn in the interpretation of cosmic ray data and for the searches for astrophysical neutrinos. There's also a huge variety of BSM and dark matter searches. And finally, if you are interested to contribute to these efforts, you're all invited to contact us because we are a very open community. If there's anything think is missing in this physics program, let us know your favorite BSM model, and we can probably test it at the SBF. Thank you very much.
Yes.
Thanks. I was a bit curious about the slides where you mentioned the fraction of swapping that you need to reproduce the data. It seems that you need something like 50% to get to the. Wouldn't that be rather unphysical? Does that have constraints from other?
Yeah, I'm not claiming that this is the final word. And here you see with 25% swapping, you kind of reach the uncertainty of Auger data. But it's probably not the entire picture, right? So it might contribute actually to a higher muon flux. But as we will see, for example, in Felix' talk, I believe in Civil Star, there are different effects, how you can basically change the muon number. I would be interested, as I said, to actually test more realistic models, because this is really a very simple toy model just to show that in principle, the strangeness enhancement can change the muon number at a level that can describe the data.
Hi, thank you for the talk. Regarding the slides like 12 and 15, you had these plots here, and here I can see PTR8 are hard or soft.
Yes. These are just different tunes of Pythia. We also actually, if you look into the paper, there's also a dedicated forward tune Pythia now. There are also, I didn't show them here because I didn't have the plots, but we tested or we made prediction with different Pythia tunes, basically.
Okay, and in a more outreach way, is there going to be another FBF workshop like there was?
Yes. So typically we have workshops every 3 months or so. We try to have workshops every quarter in the year. So I think in fall there will be the next workshop. So if you're interested and you're not in the mailing list, just send me a message.
There is a question in Zoom, I think. Please speak up.
Hello, Professor. Many thanks for your scintillating lecture. I have a couple of questions. You said these are all simulation data. How did you transform to reality with experiments? That is one question. Second question is, neutrinos are non-interacting particles, no mass and no charge. And but finally, Professor Takaki Kajita-san discovered neutrinos, and he got Nobel Prize. And what else further you want to go? You are going to discover about neutrinos? I want to know. And the third question is, if you want to do neutrino physics, you have to filter unwanted particles like electrons and muons background. How you are going to filter out these unwanted particles to detect pure neutrinos? Can you please comment on these 3 questions?
Right. So regarding the first question of the simulations, we basically just assume a certain volume of the detectors, a certain density, and then calculate the probabilities that a neutrino interacts in the detector, and we assume that we will see every neutrino that actually interacts in phasor or phasor nu in this case. And so this is regarding the simulations. I think the second question and third question was similar about what can we learn about neutrinos. Well, I invite you again to read the paper, but there are many, many things we can measure. We can measure neutrino cross-section, for example, in an energy regime where we don't have data currently to fill the gap. If I show, I think I have that in my backup slides. So in terms of neutrino physics, so here you see in the center, for example, you see neutrino cross-section measurements from accelerator data. And then at the highest energies at around 10 TeV, we actually have data from IceCube. But in between, there's a large gap, which is actually most of the neutrino fluxes in IceCube are those energies. And so we will be able to fill in that gap and actually measure the neutrino cross-sections, but also PDFs and so on in terms of neutrino physics. And I believe
what you'll use as filter to remove unwanted particles like electrons and muons background
Yes, so
in accelerators,
there are 200 meters of rock in between the SPF and the Atlas interaction point. So that actually absorbs most of the background. However, as we've seen, there's a huge muon background. And actually in the detectors, for example, at Phaser, there are veto scintillators. So you see if you have an incoming muon or if you have a particle interacting in the detector volume, and that would basically isolate the neutrino flux.
The
sorry.
200 meters, for example,
I'm
for your
sorry.
information,
Please, it's very late, so we have to go on. Thank you very much again, Dennis.
Thank you.
Now it's Ralph, neutrons in extensive air showers.